Good morning, everyone, or I guess technically good afternoon. This is a work in cooperation with my, this is the core actually of the PhD thesis of my graduate student Amir Hamedzadeh, and with Christian Gasser in Stockholm. And in fact, in this very moment, Amir is in Stockholm working with Christian on the final element implementation of these models that I'm going to present today. So, we know that biological materials are complex materials. They are multiphasic, they are nonlinear, they are anisotropic, they have a time-dependent behavior for many reasons. There is intrinsic viscoelasticity, there is the water that flows within the tissues we were talking about before, and they respond to external stimuli. So they remodel, and they grow, and they do a lot of things. One very important component of soft tissues is the collagen fiber, and it's the most common protein in soft tissues, and it's present in skin, ligaments, cartilage, and a lot of other tissues, and it's a large part typically of the extracellular matrix. And I will focus today on the hierarchical structure of collagen fibers, because this structure is responsible for the mechanism of failure of the collagen. So practically what happens is that the fibers, so this is a tendon fiber, this is a fascicle of fibers, and so each of these is a little fibril of collagen, and so that's more or less the unit of a collagen fiber, and those are linked to each other by means of these proteoglycan bridges. Proteoglycans are also another very important protein in macromolecule in our tissues, but for today, the thing I'm interested in is that they create a link between two fibers. So when this link fails, the two fibers cannot get that portion of the fiber loses continuity, and so it cannot bear any load. So this is, and I please ask you to keep in mind this J-shaped curve. This is a typical curve, not only for a collagen fiber. This test has been made by Fatzel on a single collagen fiber. And so this behavior is actually replicated at a higher scale, at the tissue scale. If you take a tendon, if you take a piece of an aortic strip and you will stretch it, you will obtain a very similar curve. So there is this sort of fractal behavior from the fiber scale to the tissue scale. And the meaning of this is that in this region that is typically called the toe region, the collagen fibers are, the fibrils in this case, the fibrils are wavy. So this is a USB cable, but for today, please imagine it's a collagen fiber. So when I'm in the undeformed configuration, this thing is wavy, and so I will have to attain a certain stretch before it gets straight, and then it can start to bear load. And so before that happens, I have no load, or very, very small load. This is typically carried by the extracellular matrix, actually. And then there is this heel region where progressively, all these fibers that have all different waviness in the reference configuration are going to get recruited, and then when they are all recruited, the behavior of the fiber is more or less linear. Okay, so please keep this in mind, because I will show you that mathematical modeling can reproduce this thing quite accurately. So the objective of this study is to build a model for tissue damage that takes into account progressive recruitment and damage of the fibrils inside the collagen fiber, and loading and unloading of a single fiber of a tissue. And then other things we want to do is to study the thermodynamics of the problem, and so look at the anisotropic damage tensor to see if there is a tensor that can describe this damage process. And then, as I said, Amir is working on the finite element implementation, and then we would like, in our dreams, to also study remodeling as a response of the tissue to damage. And we are also working on experiments. Amir, I've never done an experiment in my life. Shame on me, but what can I do? So Amir is also working on experiments, and I will show you some preliminary experimental data on these things that we're doing. So now let's go to the math. So practically what we do, we have a reference configuration here, and here we have our current configuration. So in the reference configuration, our fibril is, we look at a single fibril here, and it is wavy. And then there is an intermediate configuration in which the fiber is straight. So remember the USB cable, the fiber. No, this is the reference configuration. I stretch a little bit, I get to the straight configuration, and then from there on, I have an elastic I have an elastic deformation Fe. Okay, so I have this multiplicative decomposition of the deformation gradient. And so what happens, in one dimension, I see that this equation becomes this in terms of stretches. So my total stretch is the product of the elastic stretch that happens after the straightening stretch. So this model of fiber recruitment started from actually Christian and his group, so with Gianpaolo Martufi, one of his PhD students. And so they proposed this model, and we have modified this model to make it mathematically consistent, and then we introduced also the damage into the model. So practically what happens is that we assume that in this configuration here, the intermediate one, the nominal stress, the first pure Kirchhoff stress, is proportional to the logarithmic strain. So if you take the logarithm of the stretch, that is by definition the logarithmic strain, and so this happens in this intermediate configuration. So the first thing we would like to do is to bring this into the current configuration. So we need to do exactly what we do from the Cauchy stress to go to the reference configuration. We do a backward Piola transformation to get the first pure Kirchhoff stress. We do exactly the same thing. And so we do this backward Piola transformation. And the trick here is, since, look at this. So look at the representation of this straightening deformation. When I'm here and I'm stretching, I only have a stretch, but I have no change in cross-sectional area. That's why the other two elements of the diagonal are 1. There's no change in cross-sectional area. From now on, yes, this thing will probably become smaller by Poisson effect. So, because of this trick here, this mathematical beautiful trick, what happens is that this lambda that comes from the J, from the volumetric deformation, and this other lambda to the -1 that comes from the inverse of the deformation gradient cancel out, and so practically I get that this first period Kirchhoff stress is identical to the intermediate one. And so, if now I do a derivative with respect to the stretch, I get stiffness. So if I do this stiffness, I do my passages here. The beauty is that this thing does not depend on the decomposition. So whether, yes, the stress depends only on the elastic part, because now there is no stress, no stress, no stress, no stress, no stress. Okay, from now on there is stress. But the stiffness is independent of the decomposition. So the stiffness is the same for all the fibers. Beautiful, I don't have to look at the individual fibers. And so I eliminate this dependence and I have this relatively simple stiffness that goes with 1 over lambda. So at this point I need a way to take into account the recruitment of the fibers. And so we follow this probability distribution that has been proposed. So it's triangular, there is nothing happening up to a certain lambda minimum, and then more and more fibers get recruited, and less fibers get recruited. And at some point, at this lambda max, all the fibers are recruited, and in fact the black solid line is the cumulate, and so this tells me how many fibers are recruited. After this lambda max, of course, all of them are recruited, the value is 1. So if I multiply the number of fibers that are recruited, which is the cumulate, times the stiffness, and I integrate over the stretch, I obtain the stress. And so if I do my calculations, I get this awful expression here. But please don't look too much at the awful expression. Look at the plot of the expression, and you will see that this is exactly the curve that I showed at the beginning. And so this, the mathematical model with this very simple triangular probability can reproduce what happens in the experiments. So now, let's try to introduce our damage. So in very much the same way, what we do is, assuming that we first have to stretch the fibrils so that they become straight, and then we assume that once they are, initially some will be very wavy, some will be almost straight, but as soon as they are straight, from that point on, we assume that they're all equivalent and they all fail at the same failure stretch. So this lambda f is just a material parameter. Okay? It's all the same for all the fibers. So what happens is that I have two, can I borrow your mouse? Thanks, you are fantastic. So what happens is that I have a new probability that is exactly the same thing as this one, except that all the parameters are multiplied by lambda f. This is lambda minimum, lambda maximum, and this is lambda f times lambda minimum, lambda f times lambda maximum. So as I stretch, I get to this lambda. As soon as I get to this lambda, all these fibers here, they're broken. They are failed. So this is the probability of failure. So in my recruitment curve, I have to eliminate those fibers because they are dead. They are no longer there, they cannot bear the load. And so when I do my calculations, I use this cumulative for the fraction of fibers that are failed. And so I subtract from the total of the stress that I would obtain in the absence of damage, the stress that I obtain from the damaged fibers, and I obtain the final expression of the stress, and I get these sort of bell curve. So if I do this animation anymore, it's a little magic that Amir made. I don't know how to make animations in LaTeX. 1 minute. Yes, I'm almost done. And so, thank you. And so, as you go up with the stretch, some of the fibers are damaged irreversibly, and so they cannot be counted anymore. And then the curve goes down. When all the fibers are damaged, of course, you get zero stress. So, of course, you have to imagine that depending on whether there is overlap between the two probabilities, you have a different behavior. Of course, this depends on the value of lambda f. And so, when you have a relatively large lambda f, of course, you can get too high stresses. When lambda f is very small, it means that you are still recruiting, but the first fibers that you have recruited have already started to fail, and so you get much lower maximum stresses. We can also work on unloading. So if you unload from this stretch here, you have to consider that when you go down, you cannot consider all the fibers that have died. So you can only consider the fibers that are still alive. And so we also get the curves for unloading. So you unload from here, you go down here, you unload from here, you go down with this out a different curve. So as I promised, this is one of the curves that Amir has obtained from the experiments made on nanofiber sheets that are made essentially of nano collagen fibers. And as you can see, there is this behavior that is similar. The curves that we obtain theoretically are more symmetric. This is quite asymmetric, but we're working on that. There is probably something we could tweak in our model to make this work in a reasonable way. And so, we are pretty much done with objectives 1 and 2. As I said, Amir is working on 4, and we will start soon working on the other 2. And before I finish, I would like to thank Farah Sanjum and Elena Di Martino at the University of Cairo that has helped us with the experiments, and also the Alberta Innovates and NSERC for the funding, and the Canadian Society for Biomechanics for being so nice to give $3,000 to Amir to go to Sweden. Otherwise, it would have cost me a lot of money. And so, in case you have questions, I'm here, and provided that I'm able to answer.
Thank you.